Okay, hello everyone. Thank you very much for coming. I'm going to be talking about iterators. And of course, everyone takes iterators for granted. And we've been using them for a long time. But when we were working on our library at ThinkCell, we encountered a few idiosyncrasies that we couldn't quite solve. And we got convinced that the iterator concept is not quite the right thing to do. That it has flaws conceptually. And I will talk about this in this talk, why I think there may be something else that is better. All right, so of course, iterators have been with us since the Stone Age, right? They are modeled after pointers, essentially. Well, before we had arrays, and we were iterating with pointers over them. And then someone said, okay, we have to generalize this somehow. And if all you have is a hammer, everything it looks like a nail. So if all you know are pointers and arrays, then that concept is probably just fine, and we just got to reuse it or extend it to other data types, and so we got iterators. Now, iterators can be elements, so they are pointing at an element. Like here, you have a vector, and you try to find the minimum element in this vector, and that element is clearly 1. So this iterator is pointing at the 1 and saying, okay, this is the element that you want. Now, well, what else could there be? Well, they can also be borders. So, for example, if you have this vector, first zeros, then ones, and you ask for the upper bound of the sub-range that contains zeros, then you will get this border between a 0 or 1. And the iterator is pointing at the 1, but what it really means is the border between the 0 and the 1. And there are ranges now since C++20. And a range is really anything that has iterators. So you can iterate over them by getting the begin and the end. You can also use the range-based for loop if you like. But still, you have iterators. And these things can really be two different beasts. One are containers. They've been with us for a while, like vector, list, and set. They all own their elements, and they allow deep copying. So whenever you copy them, all the elements that are inside the container are copied along with the container. And they have deep constness. So if the container is const, then you cannot mutate any of the elements either. And then there are views. They are rather new with C++20. They are kind of the opposite of containers. They reference their elements, and when you copy them, it's just a shallow copy. So you could do the copy in O of 1, and you only have shallow constness. So the view may be const, but you can still mutate the elements through that view. So it's a bit like a value and a reference, if you will. Here is a very simple view. It really encompasses into a view two iterators, and that was essentially the old style of passing a view. You just passed two iterators to all the algorithms that are provided by C++, 0.3 already. And now you can essentially put these two iterators into one object and call it a view. Saves a little bit in typing. You get a bit more compact code. With iterators, you always had to pass two things, like you say std sort, begin and end. And when you say, okay, erase, you find unique elements, begin and end, and then it spits out, it compactifies, essentially removes all the unique elements, gives you the iterator back at the end of this compactification, and then you erase to the end of the vector. Now, this is all quite a lot of typing with begin and end. With ranges, this looks a lot nicer. You could just say sort of a vector, and then unique, and then the end, the begin and end. You just need to form this new set of these new range that you then erase. I'm seeing there's a mistake. There should be .end rather than unique.end rather than .unique and unique.begin. Anyway. So things are ranges, it becomes a whole lot simpler. This is our own library. We have it on GitHub. I'll show the URL at the very end. And there you just have to called sort unique in place, it actually solves also an interesting possible bug that was biting us, which is why we introduced it, with the ranges unique sort and ranges unique combination. You have to watch out that the predicate is actually the same, or is at least fitting. So if one has a particular less operator implemented, then the equal operator that is used by ranges unique, so sort uses less, ranges unique uses equal, and these two have to fit together. Otherwise, you don't get the right behavior. You don't get the right uniquing happening. And sort unique in place basically watches out for you that that's the case. It just uses the less operator. You shouldn't really be using for uniquing the equal operator at all. Okay. Now, let's look at some more interesting views, which are range adapters. Now, here's a classic find algorithm. It just finds the 0 in a vector of ints. Now, if I want to do something slightly else, I have a vector, but this time this is a pair, the vectors of pairs of ints and characters. And now I want again to find the 0, but I want to find it among the ints. I want to kind of ignore the characters. Then I have to write it like this without any range adapters, which is a bit unsatisfying because the two things are clearly related in semantics. I mean, we are looking for the 0, the integer 0. But syntactically, they are very, very different. And the reason for that is really that the projection onto the int, from the pair onto the int, and the search criterion, which is the equal 0, they are lumped together in the second version. And that's why it looks so different. Now, we would like to tear these things apart again so that it looks a little bit similar. So instead of like doing the find if, we are separating the two. First, we are creating from the list of pairs, we are creating a list of ints. For that, we are using the stdviews transform, and you're passing a projection function to that transform, which is applied lazily to the vector. So the vector is just referenced by this object that you return, the trans object. The trans object references vector, and when you start iterating over trans, then that object applies the projection function as you are iterating. So you don't pay for transformations that you don't really need. And there's no memory allocation. It's all, or there is no heap allocation. It's all on the stack. And then you can actually, on that transformed version of your vector, you can run the regular find algorithm with the same syntax that you use for the vector of ints. And you get an iterator out, which points at your 0. Now, maybe it makes sense. You may want, if you have your pairs of ints and characters, you may want to get the corresponding character. So once you've found your int, you want the corresponding character. And with a find if, that's fairly easy. You just have to say, oh, well, I'm getting an iterator out. The iterator is pointing at pairs. And so I'm getting the second element of my pair. And then I'm getting my character. Now, how is that with that transformed version of the vector? You have you form this trans object, and then you're finding your 0 inside the trans object. Now, the iterator that you get back is, of course, an iterator to int. It's not an iterator to a pair. So first, before we can access the second, we kind of have to peel off this transform to get the iterator pointing to std pair. So that's visualized on there. You're pointing at your first 0 in trans, and when you call .base on the iterator, it actually peels off the transformation, and now you get an iterator to the pair. All right, nice and good. Now, in this case, the iterator that's being returned by find is in the role of an element. You're pointing at a particular element that you found, and if you call .base, you are certainly expecting that .base preserves the identity of the element. So you're pointing at the 0, and after .base, you're pointing at the 0a, but that 0a is really the 0a that corresponds to the 0 that you originally found, and that's certainly the expectation here. Now, there may be, we've already talked about, that there are elements that you may return elements or borders. So if you're running upper bound, you get an iterator back, but in this case, it's in the role of a border. And then the same base has to preserve the identity of the border, because you, as a programmer, you think in terms of, okay, this is my border. If I call .base, I expect that corresponding border in my base range to be returned, and that identity of the border has to be preserved. Okay, so here it works just nicely, but well, we'll see how it goes. Let's say we have a filter adapter. What does this thing do? It's really the two important adapters. Is one the transform, and the other one is the filter. The filter here, again, we are operating on our vector of pairs, and the filter is removing all the things that have as a character have a B instead of an A. So that have an A instead of a B. So the B's are preserved and the A's are being removed. Okay, now we are again doing the same game. We transform it, and then we do a find. Okay, so now we have essentially the stack of first a filter and then a transform, and on that object we do the find. So originally we find a 0 on that filtered and transformed, and this sequence now contains only 0 and 1, because we removed the 0 of corresponding and the 1 corresponding to A, or paired with the A. Then we call .base on the transform. That gives us the element of 0b, and then .base again, which basically undoes the filter, and we are returning the 0b in the original range. Now, as you may have noticed, the 0b, of course, is not the same element that we would have found if we had executed the filter on the original range, but so without the A's being filtered out. But that's okay. We just found an identity of an element. It's not really the operation that's important. It's really the identity of the element that we found. And that element is preserved when we call .base. So everything is fine. Now, let's do the same with the upper bound. Right before we did it with the find, and now we do it with the upper bound. How does it look like there? Well, when you have only the 0 and 1, which is the filtered version of your range, you find the border between that 0 or 1 with the upper bound. And then you go back to the pairs. There, I think everything is fine. But then it becomes a bit tricky. When you call base again, of course, the iterator is still going to point at that very last element, 1b. But the border that is implied, that is meant by an iterator pointing to that element, is really between 1a and 1b. So that's a bit problematic, because this 1a wasn't really in the range that we were actually running the upper bound on. So it's not really clear where that 1a should go. Should it go to the left or to the right of the border? It was never in that sequence that we originally ran upper bound on, and that we originally looked at. So it's ambiguous. Now, you could say, well, why did you just call this .base in the first place? I mean, it's a filter, and you call .base. If you don't get a good answer, just don't do that. Okay? Leave it to the programmer to avoid these situations. All right. Okay. Here's another adapter, the reverse adapter. It's quite intuitive. It just turns the order of elements around. Okay. Now we have a transformed version of it. In this case, we find the first 0. And of course, what you would expect is you find the first 0. Then if you call .base, so you undo the transformation, that again points at 0b, which is our pair. And then you undo the reversion, and it still points to the right element. And at the end, you get an iterator of the underlying vector, which is pointing at 0b, because that's the element that was corresponding to our transformed or reversed and then transformed version of this vector. So base must preserve the identity of that one. So that's our expectation of how base should work on reverse. Now let's do the same thing with lower bound. So we are saying, okay, we want to find lower bound of the 0. Now that's a border, but that is between 1 and 0. Now, First, in the reversed version, the border is between the 1s and the 0. Now we undo the transformation, still the case, but now things become strange. What you would really want is, if the dot base is being called, is you would like to get an iterator that is pointing at 1a, because that means you are talking about the border between 0b and 1a. So that the identity of the border is still pretty clear. It's when you reverse the range. But the iterator, the dot base that before found you the corresponding element, does not find you the corresponding border. And it's not possible if you only have one base. You have to have one behavior, and you can't have two. So what do we do? First of all, let's understand why that problem occurs. When you're looking at how the reverse adapter is implemented, it really is wrapping the iterators of the underlying vector into another iterator structure, where the increment does actually a decrement. So when you walk forward, you actually walk backward in the original sequence. And the decrement is an increment. Now, the dereference is interesting because it decrements the underlying iterator before it dereferences it. And here we can see why. If you have the iterator at the begin of the reverse range, then that stores an iterator at the end of the original range. And this thing may be dereferenced because you can dereference begin, and you should get the last element. So you should get base end -1, the one right before end. That's really the begin of your reversed range. Now, for the iterator at end, the reverse is true, so it contains actually begin, but it won't be dereferenced because you don't dereference iterators. Now, if you decrement this iterator and now it's end -1, then you can dereference it. The iterator, the internal one, is then stored at begin +1, but you want to return actually begin. So in this case, in both cases, you have to decrement your iterator before you dereference it. And this is where this implementation comes from. It just does the right thing always. Now, here is really the problem. If you're looking at base in terms of element, you should really return iterator -1, because if you dereference, that's the dereferencing that you get. So when you go to base, you have to return the iterator that is dereferenced by 1. For the borders, it's okay to just return the plain iterator. So here's basically the plain conflicting requirements that we have of two different bases. Now, this problem really comes about with anything that changes the order of elements. So if you have an adapter that changes the order of elements, it's quite clear that if you have a value, right, if you pick an element, then that element is still in the other permuted range. So the permutation does not change whether there is a particular element in that range. So there is a corresponding one. You can produce a good answer. So the base of an element is well defined. The base of a border, on the other hand, is in general undefined, because if I'm jumbling all the elements, the border is kind of defined by which elements are to the left of the border, which elements are to the right of the border. Well, if I jumble them all around, then there's really no good answer where that border has gone. It's just meaningless. Now, a possible sort adapter would behave like that. You wouldn't be able to define a border base. Now, the reverse adapter is special in that regard because everything changes sides. So there you do have a good base of a border, but it's just different from the base of the element. If there are adapters that remove elements, for example, filter, then in general, the elements, they may collapse into a border. So the base of the element is still well defined because all the elements in my adaptive range are in the original range. but the base of the border is ambiguous because you don't really know where to put it with respect to the elements that collapsed into your adapter. So that makes the border of base the base of borders ambiguous. And there are a few in the standard library which do collapse elements. So there is filter, sorted intersection, sorted difference that would exhibit this behavior. Okay, there may be also the reverse. If an adapter adds elements to a base range, there kind of the reverse is true. Elements appear that were not present in the base, so you suddenly get new elements. The base of the border is actually well defined because you are just, there's still a border in the original sequence where everything that was to the left of the border in the sequence where elements were added are also to the left of the border in the original range. And the base of elements, on the other hand, is not well defined because that element may not be present in the base range. And there's just sorted union is one of these that's actually adding things to a range. So if you're basically, it's of course a binary operation, but you would, when you call base, you would have to prefer one of the sides, and then you would get exactly this behavior where a base of border is fine, but base of element is not. Okay, so now here's the problem. And now the question, what do we do? We could just introduce two separate functions, border base and element base, and then call it good. That's a small change. Unfortunately, then there's no safety against making the wrong choice. What would be a little bit better is to separate the concepts border and element. So far, they were really iterators. Both were iterators, but they behave differently under similar operations. So there's a base operation, and now it kind of depends on the role, whether it's a border or an element, what happens when you execute this operation. And this kind of indicates that maybe border and element are just not the same concept. If we do that change, we actually have no more iterators, at least in the user code and in the semantic part of our program. They're still present technically, but you would give them really different concepts in your code. You would separate them, and then you could just call base, and it always does the right thing because base knows whether it's an element or a border. Now, what I'm assuming here, or what my hypothesis is that there are really two different roles of border and element, and of course, since we have a big code base at ThinkCell, we tested that hypothesis. So we took a look: are these really are there really borders and elements in the code base? Can you, for every iterator that you have in your code, clearly say this is an element or this is a border? Okay, and here are the results. So we looked at find, when we called find, and 201 times there was a single match. We were expecting not multiple elements with the same value, but just one element with that value. And one of these finds had a border role. We really didn't mean that element, but we actually meant the border before that element. We had actually one that was actually artificially incremented to get the border afterwards. So this already shows that to say, okay, the iterator means the border before the element is that's not really supernatural. So in the program here, it's a toss. You get once we looked for the border before, and actually once we actually looked for the border afterwards, and we had to increment the iterator. And all the other ones had the element role. For 98 times, we were looking for the first match. We expected there are more than one element in that sequence with that value. 7 times we were looking at the border role, so we were really trying to find the border before that first match. 5 times we actually incremented, again quite even, where before or after, both seems reasonable, something reasonable to ask for. And all the other times we actually were looking for the element. Okay, find if. Okay, 67 single matches, all elements, 75 first matches, 3 borders before, and all the other elements All the other were for elements. Lower bound. Twice we didn't make any use of the predicate further that we were looking for. So we were really looking for the border. Now, 89 times, we actually used the predicate to find a single match. And there, so really, this is a binary search. This is not really not really a lower bound. We're really searching for a single element. And 19 times, we actually were looking for the first match. Again, there, it was the element that we were looking for. Now, upper bound, 70 times the border row, 7 times, it got decremented to get the element. So we're really not interested in the border. We really wanted the element. So conclusion is, iterator instances in our program actually have distinct roles. We can distinguish between borders and elements. Now, let's face it, iterators were always ugly, right? So begin and end are not symmetric. You can dereference begin, you cannot dereference end, and you have this funky, skewed diagram that is in every C++ book, and it's not really nice. So elements and borders, on the other hand, would look much cleaner. So you have a begin and an end, they are borders, and they sit right at the border, beginning and end, and in between you have the elements. So that looks much nicer. And then there is this abuse of end as saying, oh, I couldn't find anything. It's kind of like a singular value. So and that's for the element meaning, really. It's really kind of a magic value or a singular value. For borders, of course, it's the border after all the elements. Now, maybe we should pull these two apart as well. In addition, if we call find and then we have to check for end, we have to mention the range twice, which is quite ugly. We cannot write this whole thing in one line. And then that means if the range expression is kind of complicated, then with adapters that may very well be, then you can't just you have to put the range into a variable and mention it twice. Now, why can't we write this, right? So you just say, oh, if the iterator is found, then you do something, and iterator really, in this case, models after optional. So you can essentially you can bool compare it and you can dereference it to get your value, just like actually how you would do it with pointers. Now, so let's introduce now the border and element concepts. The border is like an iterator, but it cannot be dereferenced. And if not at begin, then it has an element before, and if not at end, it has an element after. Range, begin, and end are borders. Now, all the iterators that go into algorithm, they are describing really a range. They're really views that you're passing to these algorithms. So begin, end, input, range. The output iterators are borders as well. It's essentially the end of what the range that you've already filled, where you would now fill in more elements, where you would extend the range. And the iterators that are returned actually depend on the algorithm. Now, here are the algorithms that return borders: mismatch, search, lower bound, upper bound, equal range, partition point. They're all just one kind of very closely related group, and unique, which is there's the end of the compacted range. Now, the element concept is like an iterator, but it's never end. You cannot increment beyond the last element. And again, you can go from that element to the neighboring border with border before, border after. And here are the algorithms that are returning elements, the find and max-min element. And you would have a range of elements utility to get all the elements inside some borders. As already indicated, we really want to make element nullable, so that it behaves kind of like a pointer. And you can always we'd probably say that the null state can be reached through value initialization. And we want functions to return element they would return null instead of end. So you can write this if in a very concise way. And if we do that already, we can also go a little bit further and let the programmer encode her intent a little bit better. So right now there is the ranges find, and I already said that it's sometimes what it returns is in the role of an element, and sometimes it's a role of a border. So in the library, in our library, we have a find unique, which checks that this is really the only one during debug, but you can at least write what your intent is. You can say, okay, I'm expecting only a single element to fulfill my predicate. And then there would be a find first and find last that gives you the first or last element. And then there is a trim, which is really giving you a border. It doesn't. It takes a very similar predicate, but it really gives you a border back that lets you basically trim off some of the range that does not fulfill the predicate. Lower bound, quite similar. I already said that a lot of, or many calls of the lower bound are actually binary finds. So we have that in our library. There's a binary find unique. Again, it asserts that there's only a unique element that fulfills that predicate, or that's equal. And then there's the first and last version, and only the lower bound actually returns a border. Everyone else returns an element. Now you can always return, like use border before, border after to convert the element to the border. And yes, and the unique functions are essentially asserts. Now we can now write this thing in line, right? We don't need this end check anymore, and we can let program. Furthermore, if we wanted to do a little bit more, we can let the programmer write even better their intent by specifying what they want. So lower bound, for example, could say, okay, I want out of you, I want the border, okay? But in order to write things even more in line, could say, well, I don't want the border. I want maybe the first piece of the range up to that border. So I want the take, or I want the drop. So now when you can essentially write that first part or the last part of the range as in line, in a single line in your code. You can also get the adjacent elements, element before, element after. Now for algorithms, and that was for algorithms returning borders. Now for algorithms returning elements, we have something very similar. You have return element or null, which can say, well, if you don't find it, then just return a null. You can also say return element, which asserts if this element does not exist. So again, encode your intent, write your intent. You can get the adjacent borders. And if you don't find something, you could say, well, which one do you want then? Do you want begin or end or yeah? So that's essentially writing what your fallback should be. That proved quite practical as well. Now and then there are the versions which are essentially again giving you the prefix and the suffix before that border or after that border, and again a fallback if nothing is found. Then you can say, do you want an empty range or do you want all the elements? Now, how do you specify such a return predicate, a return template argument? Well, there's just simply structs which contain static functions pack element and pack no element. And when nothing is found, it just says pack no element, and then that would return whatever you want to return for the no element case. And the pack element return gets the iterator and the range, and then you can compose iterator and range to whatever you want to return then. All right. Thank you very much. So I'm pretty much done, and I will be around for questions. We talked about that iterators originally were modeled after pointers. It's a really low-level machine concept, and we really are in our code. We are better off thinking about iterators in terms of their meaning, their semantic concepts, elements, and borders. Because I claim that's already in your head anyway when you think about iterators. It would be nice if you could express that intent in your code so it doesn't get lost when we write code. Something that's in your head should go into the code. That distinction between the two is needed for correctness for that base function. The ThinkCell range library, and here's the URL, contains some of that already. So elements are nullable. So you can run a find in a single line. There are the algorithm refinements, unique, first, last, and there are also return specifications. We don't really have yet a strong type for border, so it means that we cannot prevent the border to be dereferenced, and we also don't inhibit the implicit conversion yet from element to border. But that would be certainly something that's nice to have. All right, thank you very much. Thank you for attending. And yes, we are recruiting. hr@thinkso.com. Write us an email. And yeah, and now I'll be around for questions. I'll ask how that's being done. Thank you.